Hello learners, welcome to Sure Question Academy. Please watch the videos, like and subscribe to the channel.
Hello, welcome back. Today, we have a very interesting and practically very important question from sound waves and resonance. Let's read it together. Let's look at part A. Imagine you have a tuning fork of frequency 256 Hz. You strike it and place its stem on a table. The table starts vibrating and produces a sound. Then, you take another tuning fork, this time with a frequency of 288 Hz. You strike it and place it on the exact same table. But this time, something special happens. The table produces a sound with maximum loudness. So, the first question is, what is the frequency of vibration of the table in the first case? And what is the reason for this? Think about it. The answer is exactly 256 Hz. Why? Because this is a classic example of forced vibration. The table is being forced to vibrate by the tuning fork. Under forced vibration, the table has no choice but to vibrate with the exact same frequency as the forcing body, which is the 256 Hz tuning fork. Now, let's move to question 2. What is the natural frequency of the table? And why do you think so? The natural frequency of this table is exactly 288 Hz. But how did we find that out? Remember, the question said the table produced maximum loudness when the 288 Hz tuning fork was used. This maximum loudness is a clear indicator that a special phenomenon called resonance has just occurred. And what is the rule of resonance? During resonance, the natural frequency of the forced body, which is our table, matches perfectly with the frequency of the forcing body. So, the table's natural frequency must be 288 Hz. Now for the third question. Why exactly was the sound heard with maximum loudness in that second case? As we just discussed, the tuning fork and the table have entered a state of resonance. When resonance happens, the amplitude of vibration becomes maximum. Since loudness directly depends on amplitude, a larger amplitude produces that incredibly loud sound. Now, in your exams, you might get a choice. Let's look at the OR question, which is equally fascinating. Part B. Imagine two children. Child A is in a small room of length 10 meters. Child B is in a much larger room with a length of 40 meters. Both of them clap their hands or make a loud sound. The question is, who will hear an echo? And what is the scientific reason behind it? The answer is, Child B will clearly hear the echo, while Child A will not. Here is the science behind it. To hear an echo distinctly as a separate sound, the minimum distance from the source of sound to the reflecting surface must be at least 17.5 meters. This distance is required because of a biological feature of our human ear called persistence of hearing. Our brain holds on to a sound for 0.1 seconds. So, the reflected sound must take at least that much time to come back to us. If we look at child A, the room is only 10 meters long. Since 10 meters is much less than the required 17.5 meters, the sound returns too quickly and no distinct echo is formed. However, child B is in a 40-meter long room. Since 40 meters is well above the 17.5 meter limit, the sound takes enough time to bounce back and a beautiful, distinct echo is heard. I hope these concepts of resonance and echoes are crystal clear to you now. Thank you so much for watching and happy learning.